Hello and welcome to the Null Hypothesis, episode number 4. Today we're going to be picking up on where we left off from 2 weeks ago with the previous episode. Sorry for the delay; I was having some internet issues, um, so we will try and be more consistent and be every Monday. But anyway, to give us a refresher here, what a null hypothesis going: H1, the Earth is in motion; H2, the Earth is stationary. And our method of determining Earth's motion and is going to be: is it the preferred frame to satisfy the laws of mechanics, the laws of dynamics, what makes future predictions of motion? And that's what physics is all about here. So we're going to read some quotes to kind of illustrate the importance of future predictions of motion based off of the energy that you put into a system so that you can solve a Lagrange or a Hamiltonian. And what those do is those calculate the least amount of energy needed to complete a trajectory. So you can plot out the future motion of an object based on what you put in there, and it will tell you it's the outcome of the trajectory there. So we'll take a look at some classic, or I'm sorry, last presentation we took a look at the classic arguments from Bennett, the bucket, the hiker, the pendulum, the train, the biker, and we have some new additions here. We have the Earth satellite slash Earth sun slash Earth moon scenarios, where we're going to be looking at frame equivalents and future predictions of motion and how those are resolved for heliocentric and geocentric positions. So we're going to get into full cosmological aspect of it too, not just lab frame scenarios. So the important thing that's going to be pointed out here in this is that there's a quote zero ordereth law of physics, which is very fundamental, and that is the law of reversibility. So, in regards to predicting future motion, you have to be able to tell, you basically have to be able to reverse the process, and without being able to reverse the process, your solution, your solution has no physical meaning. It's not in it's not in agreement with the laws of motion. Okay, so let's see here. Get into I'm just trying to give a recap real quick before we get into the quotes and stuff. So last week there was a an unresolved issue kind of that got into some circularity of the train frame analysis. So we're going to supplement that and add in a new argument to that. So we'll get into that. I got a little simulation to kind of go along with that. So we'll see how that plays out. But basically, because physics is about predicting future motion and the energy of the system, when it was asked, how do you determine what the correct, solution is? And it's the one that makes the future prediction of motion. And so we'll see how those scenarios play out when we apply that to the train frame when we try to predict future motion of the ball when it interacts with another frame. So we'll get into that, and then a question was posed last week too, for frames that give astronomical results for kinetic energy or momentum, so on and so forth. The question was posed: well, why does it matter? Can't it just be, can't why is that an issue? So we applied that to the biker frame because it was the easiest one to do it in, to show the difference there. But when you use the Earth's momentum uh, uh, to move the biker, essentially, he's going to depart with a velocity that's faster than the speed of light. So we'll see how that plays out. And the reason why why that's an issue is because that's not what is measured in the lab. In reality, the lab goes down the ramp, and the velocity outcome is based on the angle of the ramp, the height of the ramp, and his mass, and the local gravity effect. And that's what makes the correct prediction. So we'll look at some simulations for that as we continue on, and then we'll get into the new cosmological argument and stuff. So here we go with the quotes and introduction to why this analysis is valid and why it's like the backbone of physics, essentially, because it out of these equations, the Euler Lagrange and the Hamiltonian, you can predict future motion. Newton's laws of motion come out of these equations, so they are satisfying them is how you validate your theories. It's how you validate physics in the mainstream. Okay, so why the choice of frame comes first, and this comes from Leonard Susskind, who makes a couple of introductory points about predicting things and you setting a frame of reference and coordinates and what that is, and comparing different coordinates. So these are just quotes going over the importance of that. And so yeah, the job of classical mechanics is to predict the future. Classic quote from Leonard there. There are two implicit assumptions about time in classical mechanics. First is that time runs uniformly, and that the other assumption is that time can be compared at different locations. This means that clocks at different locations can place or at different places can be synchronized. Given the assumption of four coordinates of just x, y, z, t, t being the time coordinate, define a reference frame, and any reference frame is assigned a value for each coordinates. So essentially, just talking about how you're going to set up set up the equations and stuff. So there was a paper that I found where a gentleman went over about 9 different differential equations that are used to solve things from the speed of a wave in a medium all the way up to different hydrodynamic aspects that all start with a stationary lab frame to solve them. So we'll get into those as we continue here. So yeah, the job of physics is to predict what's going to happen in the future based on what you know about the system and what you know uh, putting into these equations. So when we get into frame equivalence here, we're going to talk about how the mainstream relates frame equivalence. So it was stated last week that you know you can have different frames predicting different things, and they're supposed to have the same dynamic outcomes. This is um, otherwise you can distinguish between the frames and tell whether or not a frame is truly at rest or not. It leads to a conclusion. So they all have to have the same outcomes. Um, so here, Ramirez gives the classic definition of being in a cargo ship at a constant velocity, you not being able to tell. Newton gives the similar definition of being moving in a uniformly straight line without circular motion, and that will give you the you can apply F equals ma in that frame. That's why the train frame and the lab frame make the same prediction for when the observers in the train they throw a ball up and they're not feeling any forces acting on them because they're traveling in an inertial frame. You would have to introduce an external factor for comparison for the prediction of future motion based off of the two frames to then show the difference between the two for the missing horizontal velocity component in the train frame. So just Einstein here stating in his 1905 theory that the laws by which the states of physical systems undergo change are not affected whether the change of state be referred to one of the other two systems of coordinates in uniform transitory motion. And again, in his at the beginning of his paper, he talks about how any frame where the laws of mechanics hold good or where his equations apply in. And the laws of mechanics are these equations that we're applying. And so the idea that all frames are equally valid is not going to be is going to be shown to be contradictory because it's not going to be able to make the same future predictions of motion based on the energy of the system, the momentum, so on and so forth, or any other type of violation that was analyzed during this. So like prediction of the water bending in the bucket, so on and so forth. Okay. So these claims are testable here. We could apply their mathematical framework, we could apply their logic, and we could do analysis and see which one of these frames uh, turns out to be correct without needing any supplemental fictitious potentials or anything. So this is the test that we're going to be using. This is like the metric here. So we did different types of analyses, like 5 different ones, starting with force analysis, momentum, kinetic energy and potential, and then the Euler-Lagrange and the Hamiltonian. And sometimes the frames give similar results, and then but not every frame satisfies the conditions that would allow future predictions of motion in the way that are required for the Hamiltonian and the Lagrange. So this is from Lanchos. Sorry. So he says, and this is about the importance of the Euler-Lagrange equations and how they relate to physics. This is from the book, The Variational Principle of Mathematics, going into basically how important these equations are. Yet is a fact, and yet it is a fact that these two fundamental scalars contain a that they can complete dynamics of even the most complicated material systems, provided they use the basis of used as a basis of principle rather than of the equation. So what he's talking about there is, you can have all these different variables that you need to put into a system, but the elegance of this is you just need the kinetic energy and the energy potential, and out comes the correct thing. And then as you get into things like predicting motion where there's friction and stuff involved, you can add coefficients in there, and then when you do your time integration and all that, you can figure out how those coefficients are going to affect the future motion as it's plotted out, based off of the starting kinetic energy and potential energy. And so, uh, basically saying like this is the gold standard. So the operational procedure for predicting future motion. Let us think about a particle at a point P at a time T1, P1 and T1. Let us assume that we know the velocity at that time. Let us further assume that we know where the particle will be at point 2 after a given time has elapsed. elapsed. Although we do not know the path taken by the particle, it is possible to establish the path completely by mathematical experimentation, provided the kinetic and potential energies of the particle are given for any possible velocity and any possible position. We can choose our path freely, but it is done. But once this is done, the conservation of energy determines the motion uniquely. So what I was just talking about there is your input variables are going to dictate the future trajectory path, and that is the prediction of motion. So you need to have the accurate amounts of kinetic energy and potential energy, and in the right vectors to make future predictions of motion. So Hamiltonian, same situation, but this one's momentum rather than energy conservation, and the Hamiltonian isn't time dependent, but it gives the same prediction of motion. Uh, so let's see here. So the scalar function L equals T minus V determines the entire dynamics of the given system. So like I said, once you know those two variables, the kinetic energy potential and the potential energy, sorry, you can figure out the future motion of the system. So anyway, it just goes into a little bit of that, which we covered. And now we're going to get into so like a philosophical issue that hasn't been resolved. I thought this was really interesting because I had read about it a while ago, but I kind of forgot. But there's a problem with inertia in an absolute frame. So the current mainstream physics is an acceptance of relativity theory. In relativity theory, there's no absolute time and no absolute space. So there's no absolute frame for things to be relative to. If there's an absolute frame, all motion would be relative to it. So for the most part, it's talked about like there is no absolute frame, but a little thing on the back end is that inertia is dependent on an absolute frame because an object's inertia is dependent on its rest mass relative to the lab frame. So there's an absoluteness there. Now, of course, Newton didn't know where to put he's philosophically he didn't know where to put the absolute frame because they thought that the Earth was in motion. So he thought it was somewhere in the solar system. And then Mach, of course, thought that the stars would were the answer there, that it was with respect to the fixed stars. But this is just philosophical bias because all these people also believed that the Earth was in motion, so they were ignoring the other possibility that the absolute frame is with respect to the Earth, the lab frame. So we'll read a couple of quotes here. So the inertia in question is the deepest unresolved conflict in mainstream physics. No mechanical statement can be made until inertia is anchored, and inertia is a force law that resists acceleration. The line of argument in the short language of Lanchos is three statements. Here, so we have it is the most fundamental tenet of relativity theory that force of inertia requires an absolute frame of reference with respect uh, with respect to which the acceleration is taken. So its lab frame mass, its inertia at rest, has to be taken into account for when you're going to apply acceleration to move it, and that's uh, irremovable from there. So in an absolute system, the only forces present are those of inertia and those impressed forces. The apparent forces do not exist in an absolute system. So if they're in an absolute system and we're using the lab frame rest mass of the object, and that's a pretty good indicator that the lab frame is at rest. You don't have to account for the fictitious forces acting on the rest mass or anything like that.
I have a question. I have a question for you. How can it assume that it's at rest if the body that it's on isn't at rest? If Earth is moving, then that object that it sits on the Earth is moving as well. So how can they claim it's at rest?
Oh, well, we will get to that, and we did previous analyses on rotation, so like the pendulum and stuff, where if Earth is the causal mechanism of the rotation, the wrong energy predictions are made for the swing of the pendulum. So there's a couple of different ways, and then we can get into external measurements like Michelson-Morley. Like it would take further analysis to determine that. But once we get into the cosmological dynamic analysis here, we can show that the Earth in rest is what makes the correct prediction. So
yeah, but it requires a presupposition of the action for the mechanism, right? The causality is the mechanism, which would be the action, and you're assuming what the action is to cause the result, right? The point is that to truly define what the action or cause is, you'd have to completely isolate it, and it's completely impossible to isolate any scenario.
Yeah, and as far as we can do in terms of predicting future motion is all with regards to the Earth being the lab frame, the thing that we're going to make the future predictions with, being at rest. There's no external force or any fictitious force that needs to be accounted for in that regard. So for all intents and purposes, for all these analysis, they're all showing that the lab frame is at rest. Otherwise, there would be additional energy present in the system that would need to be accounted for. That would dictate its, a change in its future prediction of motion. So none of that is present. That's the point here.
Yeah, but that would require already having a way to separate the energies in totality, right? To determine what energy is causing what effect. Because what you're analyzing is a combined energy. You don't know if it's just one source or a whole bunch of sources coming together, right? So you have to compartmentalize it, but still lead with a presupposition. You can never leave the reference frame to determine either or. It's like a snake eating the tail.
I agree about not leaving the reference frame, but the input values are relative to what you're predicting the future motion of. So if you're predicting the future motion of particles or objects that you're throwing, et cetera, it's going to be dependent on the variables of its weight and gravity. So all the necessary variables to determine what the outcome of its future motion is going to be are there. There's no anomalous thing that it's like, oh, we accounted for everything present in the system and then we got it wrong. Right? Then
well, usually it is. Usually it is.
One second.
Well, usually it is wrong because what's the sigma ratio in predictions? What's the sigma ratio in predictions? It's not very high. So they're actually, the probability of their number ratios are way off. That's why I have to keep calculating and increase the calculation length. So this is false.
Incorrect. What you're going to have to show is the system's making the incorrect predictions for motion. None of that is transpiring, and you haven't done any of that yet.
Yeah, there's a crisis in cosmology. There's a crisis in cosmology right now between understanding the micro and the macro.
Discussion section yet, and I'm still trying to get through the presentation. So if you can
I'm sorry, I didn't know that.
Continue on.
My apologies.
My point. The point is that we know all the relevant information, and we're predicting future motion based off of that. And if there was other energy or other forces present in the system, we would be making the wrong prediction. Comparing sigma confidence.
But that is the problem.
Once
you are making the wrong predictions. That's why you have a crisis in cosmology.
Oh my god, dude!
Dara, let him get through this, bro.
Finish.
He's doing a presentation.
Let him finish.
We'll do the questions after.
Not even talking about this. Yeah, we're literally not even talking about the same point at that point.
I think anyone who comes in here to try and attack Alan for having an existential crisis should automatically be put on mute. Thank you.
Yeah, if you're going to interject with nonsense, you will also be put on mute. We have information to get through, and that guy was trying to have an argument about something that's not even relevant to the subject. And if you were paying attention too, you would also want that guy to shut up so we could all continue on. So if you have anything relevant to say, save it, because the next time you do something like that, you're just going to get muted. All right, I'm going to get some water real quick. Okay, so we're talking about future predictions of motion still. We were reading some quotes from Lanchos, who wrote the variation principle of mathematics for the guide on how these equations apply for future predictions of motion and their usefulness. So here we got the Hamiltonian, which is used for these for states that the motion of an arbitrary mechanical system occurs in such a way that the definite integral A becomes stationary for the arbitrary possible variations of the configuration of the system, provided the initial and final configurations of the system are prescribed. So starting with they're letting you know where the starting frame is for these equations to solve them. So let's see here. What do we got here? We were at the inertial problem. Sorry, I got a little sidetracked there. So we were actually past that. We were on the problem of inertia and the lab frame. So two schools of thought. The Newtonian was absolute for time and space. They just didn't know where they were located. Our position is they're located with respect to the lab frame being stationary. And the relativistic physics is that time and space are not absolute. They actually change as a function of your relative velocity to whatever object you're moving to, or with respect to. And the comparison between the two is done through a Lorentz transformation, where one of the frames is treated as arbitrarily stationary, because in the definition of the inertial frame, being in uniformly transitory motion, where F equals ma, you can treat that as an inertial frame. So we can treat that as stationary. That's how they do the comparison there for that. But the fundamental backbone still, even even outside of relative velocity comparisons, they still have to start with an inertial problem here, where the rest mass is absolute. So that inertia is absolute. It's something that can't be overcome. And another extremely important part here for this is that the apparent forces of moving reference systems are of one kind. They are proportional to the inertial mass of the moving particle. Now, this is going to be extremely important later when we get into the cosmological analysis between frames. So in an inertial frame given by Newton's law, the frame is which the particle moves freely and uniformly, the force of inertia minus m times its position, its acceleration, is meaningful only in that the acceleration r double dot is meaningful in that r double dot is meaningful only when used against a reference frame that itself is not accelerating. That frame is the absolute reference frame that Lanchos names. Without it, F equals ma has no defined left-hand side. Okay. Let's see here. So, and remember Einstein's position in 1905, right in the first page of his paper, is that the introduction of luminiferous ether will prove superfluous, in as much as the view here will be developed will not require an absolutely stationary space. Yet it is still the underlying fundamental backbone of physics. So that's a pretty interesting contradiction to the relative frames and whatnot. So when we get into let's see here, where are we at? Lab frame. Just trying to scroll through here. Let me see where we're at. We should be going to, okay. So yeah, last week we did the bucket, the hiker, the pendulum, and whatnot, and the simulators aren't fully set up yet for this. So these are, just ignore this. These are wrong. Like this shows the water at rest as a curve. It hasn't been updated yet. But we do have the biker frame real quick. So we'll touch on the analyses last week that kind of got held up on, or a question was asked about, why it's important to have the correct prediction here. So we have biker going down a frame. We're going to see his velocity as his mass and gravity does the work going down the ramp versus the earth moving up to make it, to cause him to move. So if that's the case, then the momentum or kinetic energy departed on him. We can derive what the velocity would be based on that, and it ends up being greater than the speed of light. So here we go. We'll play this out. So moving at a normal speed, moving faster than c. So that's the outcome, and we know that the biker doesn't end up moving faster than the speed of light. So we can rule out that as a potential real frame that makes accurate prediction. In order to make the accurate prediction in this moving frame, you would have to introduce a fictitious potential that is the exact opposite of Earth's mass to cancel out the imparted kinetic energy on it. Because like Dude said, the proportionality of the fictitious force you introduce has to be proportional to the rest mass that you use. Extremely important concept. So that doesn't work. Now, when we get back to the train scenario here, you have the original argument where there's an observer lad in the train. He's throwing a ball up, and the ball just goes up and down. It doesn't end up behind him. If he puts the ball down on a table, it doesn't start rolling to the back of the train or anything crazy. From the lab frame, it looks like the ball is going in an arc, but in the train frame, it's just going up and down. But they're still, but they're making the correct prediction based on their definition of an inertial frame in this scenario. The only thing missing here is the horizontal velocity component of the train, which for this analysis alone is not relevant to the prediction of the ball. If we try to introduce what happens when the ball becomes detached from the frame, well, we get if we're missing that energy prediction, and we try to use the observer in the train frame, he would predict that the train's frame has zero velocity. He predicts that the ball is just going to go straight down when he releases it, and the what actually happens here is that it comes out at an arc, and so that's represented there. And then of course we can do the Hamiltonian, where we could take the energy of the system here, and the animations are a little wonky, of course, but you get the premise here. What this is supposed to be showing is that in the ball frame, I'm sorry, if you make the prediction with respect to the lab frame and you include the horizontal velocity component, you predict that when the ball hits the ground, it's going to roll with the continued momentum and speed on there. And I have I gave like an idealized surface, so it's not going to lose any velocity on impact and whatnot. It's just going to hit the ground and immediately start rolling with no loss. And there's use a low friction coefficient, so it's going to roll for 917 meters based on the energy inputs that were given there, and based on the same without the horizontal velocity component that the observer in the train frame would have, or his prediction would be that it just hits the ground and remains stationary. Now, whereas we know that the ball is going to roll with that velocity component, and likewise, suppose the ball hits a sign or something when it gets released, is the impact of what's the impact of that going to be on the sign? Well, you're going to need to include the total energy of the system with respect to the lab frame to make that correct prediction. So those are the important ones there. And then now we have the scenario here. Let's see. So Pendy. Let's do this first, and then we'll look at the simulator for the differences here. See if we can get a look at the issue. So cosmological dynamics, the heliocentric versus geocentric, the two-body Lagrange mass of the sun and the mass of the Earth substitution. There are 7 terrestrial sections for the ECEF lab frame in which the Euler-Lagrange procedure is closed natively. This selection applies the same criteria to the Sun-Earth system, and we also do the Moon and Earth and the satellite and Earth. I think the ISS. So, anyway, as we continue here, the geocentric frame also it applies the results as the same. The geocentric frame with the Earth at the origin is the frame in which the orbital Lagrange closes natively under the Euler-Lagrange procedure. This is the mainstream heliocentric description, which requires the forbidden mass substitution to reproduce the observed sidereal year when the analyst chooses the geocentric frame. So what we're going to be, to kind of lay this out here, what we're going to be going over is that's those same Euler-Lagrange equations that we were looking at when you do the geocentric frame to try and do the equivalence. So they start off with, mass of the, so in the heliocentric frame, let's start off with that. They would start off with the mass of the sun, and they would predict Earth's orbit would take 1 year based on that gravitational potential and mass that they ratio out there, for their input parameters, and that gives them the 1 year period. That's what's observed. When they put in the mass of the Earth for the geocentric frame, they get a period of 577 years because Earth doesn't have the gravitational potential to cause that period. So what they end up doing is they introduce the most important and significant solution that they try to introduce is they reintroduce the mass of the sun in the equation. So they do G capital M, and then they have little m, where they're now including the mass of the sun and the mass of the Earth, and they end up violating several mathematical principles that they have regarding covariance, invariance, and the equivalence principle, and that all frames are created equally. And so what the issue is with that is they're essentially saying that the sun's gravitational field causes its apparent motion as viewed from the geocentric frame, and that's dimensionally backwards. Like that would never be an accepted tenable position. Yet it's the only way to solve the equation and make it dynamically equivalent in the way that it needs to be. So they have to violate their principles to make it equivalent. And then we'll get into the conclusion of that, because it might be said, well, doesn't that just mean that the geocentric frame, it wouldn't work dynamically? And we'll get into the ratios used to derive everything and what it means when they reintroduce Earth's mass, because all they're doing there, instead of having it be the true mass to mass analysis on the periods, they're just revealing that it's just the same Kepler ratio of GM-M equals the basically a ratio of pi to periodicity to get the period squared is proportional to the cube of the semi-major axis. So we'll get into that as we continue on. But my contention is that the dynamic assumptions are incorrect. The principles to facilitate them and assert cosmological dominance are incorrect. And the frame, has the Earth frame has superiority because it's the frame where all the observations are made. So we'll get into that as we learn the rules here. Let's see here. So the orthodox claim is that the variational methods automatically satisfy the principles of relativity theory. So this is Lanchos was super into relativity theory. He was good friends with Einstein. So in the context that he's writing this book, it's very supportive of relativity theory. He talks about how, in the general theory of relativity, these equations of motion just, fall out naturally, for frame equivalence and whatnot. So we'll read here. So the principle of relativity requires that the laws of nature shall be formulated in an invariant fashion, i.e. independently of any special frame of reference. And this is really important here. So invariant means that a real quantity like charge or mass, when you transform it to another frame, remains the same. So remember, they did a heliocentric to geocentric frame analysis. So when their starting mass should be Earth's mass, and they're like, well, now we have to introduce sun's mass to make it match the period of what's observed. That's a violation of invariance, because mass is an invariant property.
I think what they're also stressing here, Alan, is all about the isotropy of light, and that's supposed to exist regardless of frame.
Yeah, so the laws of nature are also the laws of mechanics, and they're talking about how these laws of motion, come out of that as well for frame equivalence. Like it's not just the anisotropy; it's about the laws of mechanics. So let's see here. So the method of calculation of variation automatically satisfies this principle because of the minimum scalar quantity. It does not depend on the coordinates in which the quantity is measured in. So this is a really important qualifier of what he's saying here, because the scalar quantity that they introduce to make this work is they start with GMM, which is including both of the masses. But if you guys remember from any of the Kepler presentations and whatnot, when you have GMM over R squared and anytime you introduce GMM, the m's cancel out, and it just becomes a ratio of the periodicity. That periodicity, that's just Kepler's law. That's just kinematics. So the dynamics get reduced to kinematics by trying to satisfy the frame equivalence using the mass as a scalar quantity by combining the two. So while Newton's equations of motion did not satisfy the principle of relativity, the principle of least action remained valid, and that principle of least action is, of course, that principle that we talked about earlier that comes out of the Euler-Lagrange equations, where the future trajectory of motion comes out of the least amount of energy required for that trajectory to transpire in that system. To complete that path. That is what, because they talked about how it can calculate all these infinite possible different outcomes, but the one that you get is the one that requires the least energy in the system. So, and he's saying that relativity theory, especially the general theory, satisfies all this, but we're going to show that it doesn't. So the principle of general relativity is automatically satisfied if the fundamental action of the variational principle is chosen as an invariant under the coordinate transformation. And this is that key thing that I was talking about when they do GMM together, unlike the previous analyses where you can, where if you start from the sun frame, they don't compare the two GMs together, and that way they have them separate. They use GM sun and GM earth, separately in the equation, and it gives the correct comparison. But when they try to flip it, obviously it messes it up. So then they have to combine the two, which is where it just cancels out and becomes a ratio of the period to complete it. Okay, so let's see here. Since the differential geometry of Riemann furnishes us with invariants, we have no difficulty in setting up the required field equations. Apart from our present knowledge of mathematics, this does not give us any clue on the formulation of covariant and at the time-consistent system of field equations. Hence, the light relativity application and the calculus of variation to the laws of nature assume more than assumed accidental significance. So he's attributing this to because these work out for also the laws of mechanics, that this is more than just coincidence. This is this is evidence that space-time geometry and whatnot is true. So that's their supporting claim there. And then we went over the scalar invariance. Sorry, so that's where they're going to apply the two masses together as the starting point for the sun, and then they're going to do the same for the Earth. And then they show the equivalence by already preloading what the exact amount is needed to make the sun and Earth period the same of what it's observed on Earth, which is just the sun completing a period in 365 days. And so here we're showing this actually gets into the Kepler mass canceling out situation that I was talking about, where we have Lanchot's invariance claim requires the reduced mass scalar form. So this is what they're doing here by combining those two, is creating a quantity that's going to be invariant under transformation that they can use. But in doing that, they just return to the original kinematics, where this GM M is just a ratio of 4 times pi squared times the cube of the semi-major axis over the period squared. It's just ratios that have dimensionless ratios that are only giving meaning through comparing them to other mutually dependent ratios. So yeah, this violates their cosmological dynamics. It makes it, it renders all the claims about covariance and invariance physically meaningless if they're just going to swap in the mass like that. And then, so we got all the math for that there, but just to kind of sum it up, we should have the simulation now. So what's the end result of all that math and stuff, right? What does all that mean exactly? Well, this is what they're asserting, mathematically. They're saying Earth go around sun based on Kepler's laws, using Kepler's laws to get the ratio for GM, or GMM actually, and then when you ratio that by big G, you get the mass of the orbiting body essentially. So yeah, based on those parameters, they've set up this system where the sun is going to be like the primary causal mover in the system. But because of the way that they've attributed equivalence in the frames and covariance and all that, they require that the opposite is true dynamically. But to satisfy the equations that they use for dynamics to predict future motion, well, the period they get out of that, unless they use the sun, ends up being 577 years. So this is going to complete the slowest circle that we've ever seen, and this is what is supposed to be predicted. This is what has to be violated to satisfy what's observed. And then, of course, the same situation applies for the moon and the Earth frames. The equivalence is supposed to be provided there, but to get those periods to match, you have to introduce exactly the potential of the body that's supposed to be in apparent motion to it. Same thing with the ISS; they all produce the same thing. The frame equivalent, like determining which frame is in motion relative to one another, can be done through dynamic analysis. I think that we've shown that here. And then see if I can get to the summary here. So let's see. So the observational primacy here. So who has the more fundamental claim? Every celestial measurement is taken from Earth. The telescope's coordinates, transit times, occultation timings, future eclipse predictions, etc., all done in the geocentric frame. Doppler shift, parallax measurements, eclipse paths, all of that are done from the Earth. They're all viewed from Earth. I think they got the dynamics wrong using the assertion that Kepler's ratios. I'm sorry, asserting that Newtonian dynamics can be derived from Kepler's laws, but it's just using the GM as a ratio of what was already observed based on the period, which is just a rate. They're just ratioing in pi. So it's literally just dimensionless ratios of ratios, and they built the whole thing on that. But under dynamic analysis, the whole framework falls apart. Okay, so let me see if there's anything else I wanted to add from the notes. I think we got it all. Yeah, so the minute you introduce GMM as a single quantity, you're back to a kinematic ratio, and that's no longer actual dynamics, because you can Kepler's laws are just a ratio of periodicity and pi. They don't make any specific claims about anything. All right, let's see if there are any questions or comments. We will open the floor now.
Quick question, Alan, about the cancelling of M in these scenarios. What about paths that aren't simple Keplerian orbits? How does that fit in?
Oh, do you remember when you asked me this on Twitter and I gave you a spreadsheet of different orbits, binary orbits? No,
I'm talking
equal. What ones where they were almost equal? Like, what's the issue?
So I'm talking about paths that aren't simple Keplerian orbits. So things like trajectory planning and stuff like that, where it's where the object is not traveling purely.
Roboting pretty bad.
No, you're fine.
Sorry, my microphone.
So are you talking about like Artemis or something like that?
Yeah, something like Artemis. Yeah, where you have a trajectory that is not a Keplerian orbit.
Yeah, perfect. Yeah, so they used
There's
all GM ratios. Yeah. So they didn't do any of that, and they just used Kepler ratios for the whole thing. I have a whole workup on it. I'll send it to you.
I don't think they did. Initially, they do it with.
Hold on a second, Asa. Hold on a second. I don't think they did is insufficient. I'm about to drop you primary sources of exactly what they did, and they just used GM in the exact same way that I said it did, where it's just a ratio of Kepler's laws. So give me 1 second. I'm pulling that up for you.
Yeah, I think I've seen that.
We're not going to entertain. I don't think they did. You have to substantiate what they did and show that, because I have evidence to the exact contrary.
So I'll give my understanding of what they do. So initially,
your understanding is unnecessary. Get Daza. Your understanding is unnecessary. I need primary source documentation of your understanding means nothing. I have primary source documentation backing up my point.
We can discuss your documentation then. I think we'll be in alignment. So they use an approach called patch conics initially, right? Which is a whole series of short Keplerian segments.
Okay. So we're going to disregard what I said.
No. If you let me finish, right?
And we're just going to start repeating your thing.
So they use a Keplerian approach with a method called patch conics, where you've got all these little interconnecting segments that are approximately Keplerian orbits, right?
Here.
Then you have a gravitational
trajectories.
Yeah, I've seen this page, and this is what I'm actually discussing.
They don't use anything like what you're saying. The best case scenario that you could make is they make gravitational perturbation correction or whatever. They don't even do that. They make velocity dependent corrections based on timing. So at no point is there any gravity being accounted for. So listen, I'm not interested in your understanding. I need primary documentation from you, because you will often say random things that are not true at all.
So
you do it too many times, and I'm not here to waste time. So
I've read your documentation that you've just linked already, right? And so two things. So one is the each phase of the trajectory that's discussed in your document, you're going into the sphere of influence and stuff like that. This is the patch conics approach, where each little tiny segment is treated as a small Keplerian orbit, right? So you have those periods. But when they do the numerical integration of the precise path, it is done across the acceleration field, which is based on GM and R squared. So it's a multi-body field.
That's my premise. The GM R squared is just kinematics based off of period. That, like you just restated my exact point, man. Like we just went through all that to get to the same point. It's not. The GM is the Kepler ratio. It's never not that. Like this whole thing is filled with citations that go over exactly what they do.
Yeah, but like the numerical integration step is based on a potential field, right? That if you put any object in that potential, it is.
Deza, GM is proportional to a period. It's literally a ratio of a period.
That's your interpretation, right?
It's not an interpretation. It's a mathematical fact.
You don't have to have something traveling with a particular period to have GM applied, right?
It's a literal.
Kepler's law.
Yes, it's
Kepler's law is not the only place that GM appears, right?
If
I'm not traveling
from one another,
a circular orbit.
Daza, they're inseparable from one another. If there's a GM, that's automatically Kepler. It's right there. It's not my opinion. They're ratios. The GM is a ratio of the of what was it, 4 pi squared times the semi-major axis cubed over the period squared. It's always that. It's never not that. It's not my opinion. It's your opinion that it's not. You can't separate the kinematics from the dynamics. There's no prediction that you can make that's mutually exclusive using this orbit if it includes GM. So when you say like, I'm going to go over my understanding and all this stuff, none of that is necessary. You just need to show where they would actually use mass, right, and gravity not together as a ratio of Kepler's laws. Because you're saying that this is a multi-body problem, but they're just ratios of velocity components. So how they integrate it over a field and try to whatever is irrelevant. The ratio is always there fundamentally. It cannot be separated. I'm going to unmute you now so you can get your closing thoughts, but that's it. There's nothing else. Go ahead.
So I would agree that in the case of a Keplerian orbit, the GM is the ratio, right? But in a multi-body system, GM, this is big M, is used to construct an acceleration field, right? So your little m cancels and you get this gravitational field, which is what is used to do the numerical integration to find the final path. And that path has, maybe GM was derived from the periods initially, but the path itself has no periodic component like that in it. Each integration step is purely integration across the vector field.
No, the m cancels out because it's not relevant. Like they would say that it's too small. So it's actually always GM. It's never just GM. And based off of that GM, like so if you give me the component, like the thing is like what you're talking about is in this thing here, all the GMs and ratios are all backwards derived to show what the periods and stuff are. So it's never not that. Just a GM, like saying just GM as one isn't different from GMM. They're the same. But the term cancels out. So most of the time they talk about it as just GM. That's how we look at it in familiar terms, but it's actually always GMM.
So I agree with you.
Because when you do, so you don't like, that's let's see here. There's even a workup here on the approximation from it. It's called let's see, a second.
So I'm not disagreeing that the best values we have for GM.
It's called the Bate-Mueller-White approximation. So the mass of the orbiting body M will be so much less than the mass of the central body, hence that we see G plus M, big M and little m is approximately GM. So again, this integration over a field, all this stuff, it's never not the same Kepler ratio. Now, Daza, we're going to move on now. And the next thing you can do, like next presentation or whatever, is you can try and show mutually exclusive instances where they're not using a ratio of Keplerian kinematics to describe position and time. And where changes need to be made, because that's my whole point. It's just kinematics. It has nothing to do with the actual forces. GM is Kepler's ratio. GMM is Kepler's ratio. It's always the same. It's just written approximately because the other m always cancels out anyway.
Yeah. I'm not denying that, right? That the GM is Kepler's ratio, and the best values we have for GM for any two-body system are based on observing Kepler's laws, right? So we get very good values for GM, even if we don't know what G is or M is independently. But in the case of multi-body systems, where we have multiple GM combinations across multiple bodies. So, the moon, the moon orbit, or orbital segments where the moon dominates, there's a different GM to the Earth dominated one, and there's a sun dominated one if you're in the right spot. So all of these orbital things have their own unique GMs, right? But they all come together to form an acceleration field where GM still exists. The m's are all different, but the g's are the same. The mass of the object is not important because it doesn't alter the positions of those other objects, which is why we can keep it constant. And that's what the acceleration integration does.
Yeah, so there's not even a three-body solution, and the way that the whole thing that works, and the reason I'm asking you for primary sources is because you're just saying things. You're just saying what you think and what you imagine it to work as. It's literally like I have the primary, like DAZA. We're now moving on. Like this is insane.
One more comment about the three-body. You're right. There's no analytic solution for most three-body systems.
You're not going to talk over me in the middle of the thing, dude. So the primary objective here, right, was future predictions of motion. Okay, there's no future prediction of motion in the line of what you're going down, DAZA, that is mutually exclusive to dynamics. If it's GM, you already just said yes. I agree that GM is the ratio there, and then you're like, but if we add them all together, it becomes a different thing. Who even does that? That's not even. Show me where they're doing that, because that's otherwise you're just talking. This isn't the place to just talk endlessly. So back to dynamic predictions. There aren't a single one that's been mutually exclusive with respect to some other moving frame that satisfies anything like the way that the lab frame does. And the violations of what was going on over the invariance and mass situation where they substitute the sun's mass in using GMM, using the full GMM written out, not just the approximation. And the full GMM gives you just the Kepler ratio, as does just the regular GM, as noted by the citations that were given here for the Bate-Muller-White approximation, the mass reducing. So the reason all these work is because the other M cancels out. It reduces back to the original Keplerian kinematics to satisfy the so-called dynamic predictions that should exist through the equivalence principle, satisfying the general principles of covariance, so on and so forth with relativity theory. None of those satisfy anything that's been brought up here.
It's now an okay time to ask a question.
Absolutely.
Hello, sorry, my normal headset died, so I was trying to find a different one. Am I coming through okay?
Mm-hmm.
Hey, sounds good. So I was interested. First of all, thank you for presenting. I was interested in the slides you were showing where you were talking about modeling the sun at the center with the Earth going around it, and then switching to a perspective where we're modeling the Earth at the center and the sun was going around it. And I wanted to make sure I understood what you were pointing out there. And my understanding so far was that you were pointing out that if the Earth goes around the sun at a certain periodicity based on the gravity from the sun, then we don't in any way get from the gravity from the Earth that it would make the sun orbit around it at the same periodicity. Is that a fair understanding of what the point was?
Correct. It leads to different dynamic predictions.
Right. So placing the Earth as the stationary point does not fit with the dynamics of Newtonian gravity. Having the sun going around the Earth is not compatible with Newtonian gravity.
Or relativity.
Well, so that was my next question there, which is why is this a problem for relativity?
Frame equivalence and the what we just read at the beginning of Lanchos talking about how the future predictions of motion, fall out of the equations due to the equivalence principle and the theory of relativity, or I'm sorry, the general theory of relativity. So the way that he's applying them in equivalence and arguing it is exactly that the frames are going to make the same dynamic prediction.
So I want to go back to that because there was a really important qualification in saying that different frames will give the same predictions. That was specific, though, to frames that are moving in linear motion to each other. So if we said that the sun being stationary is a valid frame with the Earth going around the sun, and then the fact that the Earth is going in a circular motion around the sun seems to rule out the Earth being a valid frame.
How so? We observe it from the Earth perspective of the sun going around us. Like the position that Earth partakes in the period is like a secondary thing. We observe the sun going around us. So to say that the Earth partakes in it is a secondary thing. But the main important part here is that they've facilitated things in such a way that like what the qualifier was explicitly, right, and the fact that the equation applies one way, you know, it doesn't all of a sudden make it invalid when we try to do it from the Earth frame, because when you do it from the Sun frame, the Earth's doing the same thing.
No, but the point is that what you read at the beginning was that if we establish that the laws of Newtonian mechanics do work in some particular frame, they will also work in another frame that is moving at a constant linear velocity to the first frame. But there was no guarantee in the first thing you read that they should work in a frame that's doing circular motion within the first frame.
Well, as the overall dynamic cause of motion in the greater general relativity universe theory, the Earth's actually in free fall around the sun, and it's classified as it being in an inertial frame. And then when you get into satellite predictions, they're in free fall around the Earth, and the Earth is an inertial frame, and the satellite in free fall around it is also considered an inertial frame. So they're defining the inertial frames and applying the equivalence principles through different types of orbit, depending on what your preference is. Or is it going in a straight line, falling around curvature, or is it traveling in a straight line that's just a big circle, but it's so big we can just treat it as a straight line, so on and so forth. There's different people have different preferences for that, but the main important part that isn't, that's kind of being not addressed here, is that when we show this equation for the heliocentric frame, it has no problem with the circular thing, but when we apply it for the reverse, all of a sudden it's a different thing and has to be discussed different. So none of that is valid. It's not a
No,
valid take.
so what you said there is very interesting about general relativity, but that's because general relativity is making a much more radical claim than Newtonian dynamics was making. So like, yeah, you're entirely right that general relativity goes much further than Newtonian dynamics goes in claiming that any freefall frame, even if it's doing circular motion, can still be treated as an inertial frame. But that's not true for the Newtonian model. In the Newtonian model, the Earth isn't treated as an inertial frame.
Well, it actually is treated as an inertial frame because it's in uniform rectilinear motion, and that's why we don't experience any of the forces as we go through space. So they treat it as that, and then for all experiments, they treat it as,
Under
it's
general
relatively
relativity.
no, under Newton. Newton literally defines an inertial frame as being a uniform rectilinear motion at a constant velocity as well.
But I mean, orbit's
Einstein
not
borrowed from that.
linear. Like a circular orbit in Newtonian motion,
he was describing it in the context of Earth's velocity around the sun. So
which is a circle in the Newtonian model.
And he described it as an inertial frame, bro. Anyway, so we have this issue here where the principles of covariance are being violated. We have an invariant quantity being substituted with another mass to cause the apparent motion. The dynamics are and then when you do that, when you include that mass to complete it, you're actually just reintroducing Keplerian kinematics, because it's just a ratio of the period, which isn't mutually exclusive to anything, and it just defaults back to where the observation was made from, on Earth.
The point I'm making is that if we're strictly speaking, sticking to
can you address the point that I just made so that we're not talking past each other? Because what you did is you tried to say that the Earth isn't defined as an inertial frame, but when we just went over instances and where it is, and in the context of which Newton was talking about the Earth as an inertial frame, defining it as that uniform motion that's not changing very much. So that's same scenario, and then you're like, well, now I have a different point, and so we're getting further and further from a conclusion.
I gotta get the door.
Further and further from a conclusion. Okay.
I'd love to cycle back because I gotta get the door. Someone's here.
You're good. Go ahead. We'll cycle back. But yeah, we're getting further from the conclusion here. The general point being made is that Newton considered the Earth inertial. You can show that the Earth's inertial through Newton's bucket, all the other stuff that we did. So the definition, but the definition that they were applying for the uniform motion was in the context of the Earth going around the sun. So it can't not be an inertial frame when you don't want it to be. Like
he describes it as going in a straight line, right, Alan? Newton.
Yeah. So in special and general relativity, straight line. In Newtonian dynamics, right? He just took a ratio of Kepler's laws and said that the G and M that comes out of that, because they didn't have the G yet to actually get what to isolate the M and stuff out of it. So they just had he just had these ratios, and he was like, this is probably the cause or whatever. Like, he didn't do anything different. There's not like a different prediction. He didn't arrive at it differently. He took the already existing ratio and then did another ratio of that, and then said this is probably the cause. And then so, regardless of how it's defined in equivalence and whatnot, the current standard of mathematics and all of that is based off of these principles. So if general and special relativity are shown to not be true, and we show that through the other analyses that the Earth is an inertial frame, then as defined by being stationary and fixed, then none of these cosmological kinematics mean anything, because the big like trick here, right, is when they reintroduce that Earth's mass to it and make it GMM, they're fully just like reintroducing the Kepler ratio. They're making it so apparent. Like the other equation, when you start from the sun frame and ratio it, you're ratioing the GM of the sun and the GM of the Earth separately, not in the same way where they're combined by GMM together in the same string. In the previous analysis, it's only when they do the heliocentric frame they recombine them together to get the same period, because they can't arrive at the same period. So when they do the dynamic analysis, the like in reverse, right, starting with the sun, and Earth separated, because Earth's mass is so small, its gravitational field, its influence is so small, it doesn't change what the sun is doing towards it period wise. Because remember, it's like the factor difference between the influence is 330,000 times difference. So if it takes the Earth 577 years to move the sun, but if you just accounted for the mass of the sun to do it, well, this tiny amount here isn't going to change the period enough to matter. So that's why it works for the analysis separately when they start with the heliocentric frame and do it separately. But when they try to show that the equivalent is true, that's when they have to violate all their principles.
Let's say, sorry, I had to jump up there at a bad time in the conversation. Door rang, dog started barking.
No worries, lad. We were just discussing the reintroduction of the mass component to fully complete the cycle.
You had a slide there showing 3 different things that. Can you bring that up? That looked interesting. You just passed right by it.
Are you talking about this one right here?
No. Before that, you had there was 3 contradictions, and I usually talk about dialetheism, so it reminded me of trialetheism. They had a name like tri something.
Oh, the trilemma.
Yeah, there. That's the one. Yeah.
I got you. Mainstream physics holds 3 claims simultaneously. All inertial frames are equivalent, Galilean/Einsteinian relativity. The heliocentric and geocentric frame should return the same physical prediction for the same observable. 2, the mass and frame invariant scalar. So this is what I was talking about earlier, where your starting mass under transformation has to be the same. So in order to get GOC and helioc equivalent, they have to start with GMM included together, where Earth's M just cancels out and it just becomes the Kepler ratio that they always started with. But in any case, so the mass invariant scalar, so the mass sun stays mass sun, and mass Earth stays mass Earth, regardless of the frame. So remember, when you do the analysis where these quantities are separated and then ratioed, it produces the correct period. But when you start with the Earth frame, it doesn't work. You have 577 year period. It's only when you introduce them together as a, what do they call it? I want to say scalar quantity, but I don't think that's correct. But anyway, they have to introduce them together is the point here. 3, the 2-body Lagrangian carried through without substitution gives the position is equal to minus GM sun over R squared in the heliocentric frame, and the position is equal to GM or minus GM Earth over R squared in the GOC frame. These different predictions by a mass ratio of 330,000. That's the difference of influence between the two. So any two of these can be held simultaneously, not all 3. Mainstream holds 1 and 2 publicly while violating 3 and using rescue techniques cataloged in section 3.4. The violation, and that was where we went over, it's just an approximation, the standard of reintroducing the mass of the sun to begin with in the GOC frame, so, all that kind of stuff. It's all basically the same thing. The violation is a structural admission that the frame equivalence is false. The frames are not equivalent for the orbital Lagrange. The GOC frame, where Earth naturally appears as the central gravitational force. Section 2, the frame answers the same for the terrestrial mechanics, and the frame for the Euler-Lagrange procedure selects both terrestrial and in the cosmological procedure selects in both terrestrial and the cosmological case that the Earth is the Earth-centered lab frame. The old trilemma, you like that, SE?
Oh, I love that one, bro. I love that one. Triletheism. Yeah.
So if I may ask again, just the clarifying question here, I think the thing I'm having trouble tracking here is what is the definition of inertial we're using? Because Einstein had a very different definition than what Newton did. And Einstein was putting forward a fundamentally new basis for how to define an inertial frame.
Second, we'll pull up exactly what Newton defined it as and exactly what Einstein defined it as.
Thank you.
1 second. 1 second. So let's see if
Only one of those two guys uses the term curvilinear.
Yeah, I wonder who.
Okay. So let's see. Classic physics, Newton, absolute motion. This is from Greenwood, Principles of Dynamics, 1888. So this is Newton's laws apply to motion relative to this frame. It can be shown that for any other frame that is not rotating, but in translating motion uniformly and with a uniform relative velocity to an inertial frame itself is an inertial frame. So moving in uniform transitory motion, that's not anything different than what was being described there. And then for Einstein specifically, get into lecture.
So Newton, it's uniform transitory motion, right?
Yep. Mm-hmm.
Okay. So
Yep.
that doesn't
Einstein,
apply to an orbit.
the orbit is so big that you're basically moving in a straight line. And
Hence
also,
my comment.
it does apply.
But that's,
also,
I mean, that's a question of approximation over small timescales. Like sure, you
That's
can say
dialetheism. That's what that is. Two things. You're thinking of two truths right there. Traveling in a straight line, but it's curving.
So, of course, we could say over the course of an hour under Newton's model, the orbit of the Earth is approximately a straight line. But over the course of a year within Newton's model, the orbit of the Earth is a circle.
So
There's no straight lines in an orbit, though.
In any case, none of this falsifies the null hypothesis or shows that that we gave an incorrect definition for something. So, like, what we're showing here is that the Kepler ratio, right, which is just periodicity and pi, and then the Newtonian dynamics that followed that lead to the analysis and everything, and all this equivalence and covariance and whatnot, is physically meaningless. It can't be satisfied under the conditions that they give, and the initial ratios are just kinematics. There's no Newtonian prediction that can be satisfied that's separate from a kinematic ratio of Kepler's periodicity and pi.
I'm in any way debating the whole point about the mass dropping out point.
Okay.
Yeah.
Okay. Well, that is the purpose of the discussion, please. So,
well, I was trying to understand what you were doing in putting the Earth at the center of the reference frame for an entire year as we'd watch the sun perform, or entire day, whatever the extended period of time was, to have the Earth stationary with the sun doing a full circle around it.
Showing that the frames are not equivalent when you try to make dynamic predictions.
Agreed, they're not equivalent. Definitely not. The Earth is doing a circular orbit.
Actually, it's not circular.
Elliptical, whatever.
And there's also a speed change in that.
So real quick here, the Earth's in an elliptical orbit. Incorrect. That's just determined from the ratio of periodicity of Kepler's laws, of us just watching the Earth. To assert that Earth is the one that's partaking in the motion is a separate hypothesis that hasn't been substantiated. You haven't led to a single prediction that leads to a mutually exclusive outcome other than having to introduce the same Kepler ratio to make it to make the dynamics equivalent. So,
isn't that their claim, though, Alan? That it's an oval orbit; it's not a circular orbit.
It has a slight eccentricity to it. It's basically a circle. I mean, essentially, but it has like a slight deviation from a circle.
All orbits are elliptical,
But
even if they're just slightly.
Sure. But they claim multiple different things too for the orbit, right? So they'll be like, well, it's going around an elliptical orbit, Kepler, Newton, and then they'll also be like, but it's traveling in a straight line in flat space.
Yeah, right.
Like, well, and then they'll be like, well, it's also free falling through the curvature of that space time in a different, through different aspects of it. So it's like three different ways to talk about the orbits in ways where it can't be quite tied down. But here we're showing with the dynamic prediction that nothing satisfies it.
But you're skipping from
simply saying that the Earth is an inertial frame because it's going around the sun for all intents and purposes, and for the laws of dynamics, which we're using to make the predictions of motion. No other velocity component is required to make any additional adjustments. In fact, you could even take it further when you get into light and atomic clocks and satellites. There's something called the midnight noon problem, where a satellite on the facing the sun at noon will have a different gravitational potential based on the gradient of the sun. As we're moving through the orbit throughout the period of the year, is going to be different than when it's on the other side of the Earth at midnight. And no clock adjustments ever have to be made for the tune of that. There's no dynamic repercussions for not accounting for any of the supposed motions or gravitational influences of other bodies.
Well, absolutely. I'm not.
No, I'm talking to Z-Pop, and like to turn around and be like, well, it's not an inertial frame because it's going around the sun. That's your assumption yet to be proven, sir. That's what we just spent the whole dynamic presentation showing, that the Earth being stationary is what makes the predictions correct, not anything else.
Well, I'm just recalling what Newton said an inertial frame was versus what Einstein said, and trying to figure out what we're talking about here within this conversation. Because you're right, according to Einstein, the Earth going in its orbit around the sun would be called inertial, but according to Newton, it wouldn't. Newton would have said it's approximately inertial for a very brief period of time if you can pretend the ellipse is a straight line, but Newton would have said that the full elliptical orbit is not an inertial reference frame. So I'm just trying to understand which definition of inertial we're using here.
You just said pretend.
So listen. The current mainstream paradigm is that we can't have three separate orbits, right? Where it's a circle / ellipse, or it's a straight line, or it's a straight line in free fall, right? These are all contradictory, different things, different levels of causal mechanisms inserted in. But to identify the definitions real quick, right? The examples of this sort, together with unsuccessful attempts to discover any motion relatively to the light medium, suggest that the phenomenon of electrodynamics, as well as the mechanical processes, which is what we're talking about, the future predictions of motion, so on and so forth, possess no properties corresponding to the idea of absolute rest. They suggest rather that as has already been shown to the first order of small quantities, that the same laws of electrodynamics and optics hold valid for any frame in which the equations of mechanics hold good. The equations of mechanics are the Euler-Lagrange, the force equation, the kinetic energy, all those ones that we were doing our analyses with. Those are the equations of motion. The equations of mechanics. And we're seeing in what frames those hold true in. So Einstein says that it's true in all of those frames. Even if Newton had a different definition for Earth's frame, we already showed that to be contrary. We already showed that the Earth satisfies all of them, not as an approximate stationary frame, but as a stationary frame.
Not according to Newton. The Earth doesn't satisfy the inertial
frame. Dude, completely irrelevant. I satisfied it through all the laws of dynamics, all the ways of predicting future motion. I could care less what Newton what he thought about it. I showed it with using his own principles. That's a philosophical difference.
No, Newton said inertial reference frame was straight line constant motion.
And yes, and even so, even if that doesn't apply to what we're talking about with the Earth, right? Even if it has a different definition, what I'm showing is that the actual definition of being inertial is that it's stationary. So adding additional supplemental things about the Earth being in motion is something that you would have to prove through dynamic analysis, not just simply questioning what constitutes an inertial frame.
What dynamics are we talking about?
Back, I'm gonna get some water, dude. What dynamics are we talking about? We're here for the entire Prezi. So the dynamics we're talking about are the predictions of future motion. We're predicting future motion.
Like a ball on the Earth, or the Earth going around the sun?
I gave all the scenarios and all the math for it, and we're now detracting back to nothing. If you'd like, I can send you this HTML. You can read it, and on the future null hypothesis presentation, you can go over and ask questions and whatever, and get the full scope of it. Because as someone who just went through the whole thing, and then to be asked, or what are we talking about, is like I'm not going to do that,
Well, what I'm saying is that what
Like,
Newton said
well, no,
was
well, no,
that.
no, 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 no. What you're saying is that you just asked me what we're even talking about.
Well,
So
which
like you don't
scenario?
get to you don't get to see you don't get to say anything now.
No. I mean, which I saw your scenarios. I mean, which scenario? When you referred to dynamics, and I said, which scenario are you referring to right now?
The same scenario that we've been referring to.
So the Earth orbiting the sun.
You're saying Earth orbiting the sun, but the sun's period around the Earth, or the Earth's period around the sun, is a kinematic assertion, and that's what the dynamics had to fall back on to substantiate their claim. They had to introduce full-on kinematics. So trying to revert it back to the Earth around the sun, is just rhetorical nonsense at this point.
No,
We
I'm
did
asking.
all these analyses. Hold on, we did all these dynamic analyses showing that the Earth is an inertial frame as defined by stationary and at rest. Okay,
So
not a single prediction
I think this is tremendously
came out.
important to get clear on for me, so I understand what you're saying. Because what Newton said was that for, let's say, a ball bouncing up and down on the ground of the Earth, we could treat the Earth as basically inertial. But for the Earth going around the sun, we cannot treat the Earth as inertial.
Treat it however you want, right? I don't care. In the current mainstream, everything that's backlinked to that based off of Einstein's general and special theories is contradictory. Okay. Now, as far as Newton goes, as defining his philosophy on Earth's motion, that's irrelevant. We showed that all the predictions made are just kinematics, right? So saying Earth's motion is based off of Kepler's ratio, it's just kinematics. It could go either way. There's no dynamic cause, inertial or not. That is the key point of this. You getting hung up on the definition of inertial and whatnot is a non sequitur, and it's kind of getting annoying at this point.
Well, that's the whole crux of this, because the laws of physics only apply to the inertial frames.
Yeah, and I gave 7 different scenarios where they only apply, where the Earth is consistently making the correct prediction every time. The Earth at rest frame, and then on top of that, there's like 9. Yeah, there's 9 field. There's I forget how many. It's like 7 or 9 field equations. A wave equation for a vibrating string. Hooke's law. Kepler's orbital equation, the sound wave equation, the heat equation, Schrodinger's equation, Maxwell's equation for light, the historical take, all start with a preferred frame at rest to make future predictions of motion. That's what we're talking about. That is the core subject. So to falsify the null, you have to show where the lab frame is making the incorrect prediction. Now, cosmologically, we shattered the dynamics, showing that they have to reduce the kinematics to satisfy them. If you have to reduce the kinematics, that's non-mutually exclusive. So in every other scenario, go ahead.
This is why it's important for me when I said what dynamics, what scenario, because if we're specifying scenarios like waves, electromagnetism, Hooke's law, all that stuff in a lab on the Earth, I 100% follow and agree with you there that saying that the Earth is inertial gives the correct dynamics for all of these small objects we're looking at here in the lab. I was specifically asking, when you showed the Earth as being stationary with the sun going around the Earth, what was the purpose of what was being shown in that scenario is what I'm trying to ask.
To show that the dynamics don't make the same prediction and that you have to introduce a kinematic ratio to satisfy them, which violates the entire top-down structure of general and special relativity. So the point is that when you show this in the heliocentric frame, everyone's very happy and excited because it gives the period for that's observed. When you introduce it to the geocentric frame, it doesn't work. You have to smuggle in the Earth's mass, fully completing the Kepler ratio, which just makes it kinematics. So the idea that these dynamics lead to mutually exclusive predictions, therefore Earth go around sun, is not true.
Anyway, I agree fully with what I took away from that example, which is that sun going around the Earth does not work within Newton's laws of physics 100%. So if that was the purpose of bringing up that example, then I don't think we're saying different things or have any disagreement. I just was, when we went from examples of looking at dynamical systems like in a little laboratory box here on the surface of the Earth to looking, like zooming out and looking at the Earth with the sun going around it, I was trying to understand how that fit into the larger set of scenarios you were talking about. But if the main point is that Newton's laws do not give accurate predictions if you say that the Earth is stationary and have the sun going around the Earth, then we're saying the same thing, and I entirely agree.
it's not that they give inaccurate predictions, it's that they give a kinematic prediction that's not mutually exclusive. It's just a periodicity that's a ratio of pi. So the whole buildup starting from Newton and then going into general and special, or special and general relativity, and doing the analysis through the way that mainstream interprets equivalence and the laws of mechanics and future predictions of motion being those laws of mechanics, we showed that the lab frame, like in no scenario do we have to account for so-called Earth rotation or Earth moving around the sun, right? And then we moved it to the cosmological differences where we do the analysis based on the gravitational influences that they say are equivalent. None of that works out, and the fact that they have to reintroduce the masses as the full Kepler ratio just reveals exactly what it is. It's just a ratio of pi and periodicity. So saying that we're going back to what Newton determined as a reference frame and whatnot is irrelevant to the point that Newton's dynamics are just ratios of Kepler's kinematics, and the kinematics are not mutually exclusive to motion. And everything that we've shown thus far is that the Earth is stationary, and it's the cosmological dynamics that are off because those come out of a ratio of a periodicity. The ratio of periodicity can't be wrong, right? It's just pi and period. So it works for whatever. It's only when you take the ratio of that and try to assert that that's the dynamic cause of the motion and build a whole cosmology off of that, that is where it's shown to be contradictory and physically meaningless.
I definitely want to give other people a chance to get questions and comments in. Thank you.
Okay. I'm going to go grab some water. If anyone has any questions, I'll be right back, but go ahead and spit it out and then I'll return.
I just want to say, like, the notion that the Earth can be considered an inertial frame, right? Even by their cosmological model, an elliptical orbit, it changes speeds, right? At the aphelion and perihelion, where the curve is. So it's not possible, even in their model, to consider the Earth inertial.
Yeah, that was.
I think it changes. It changes so slowly over a year. Like Stone's got a video on it that shows how it all works. It's like a 3 or 5 million velocity difference, but it's like gradual over the entire year. It's basically nothing. So in any case, if there was like, it's like, show me what I have to do to incorporate that motion as a prediction for future motion in any scenario. It's like it can't be done. So
right, I'm just saying, like, technically,
yeah,
it cannot be considered inertial, but by their own standards. I'm not saying I believe it, but I just feel that's important to point out.
Yeah, they often try to have it both ways.
Exactly. Dialetheism.
That's quite a drastic change. Imagine going from 1 mile an hour to 3 million miles an hour. But ZZ Pop, were you going to say something?
No,
I said 3. No, hold on one second. Yeah, I way said
it. Ellen, you're back.
The velocity's way off. Yeah, that velocity's way off. Sorry, it was okay. It's not that drastic.
Thank you.
I think it's important just to point out those contradictions because they have a lot of them in their cosmological pseudo model.
Yeah, it's like the Earth's inertial except for when we swing a pendulum or whatever, and then all of a sudden it becomes non-inertial. but for like the tiniest particle, prediction, so on and so forth, it's it's fine.
Yeah, the idea. Oh, go ahead.
No, go ahead, Eden.
Oh, thank you. Yeah, like I'd like to continue to explore this idea of the sun falling in space because it's a really interesting concept that I think we could probably explore where we get to the point where we think it's illogical. But what do you guys think?
Bro, everything is falling in their pseudo model. Everything is falling around something else. And all falling around the great attractor, which I make fun of all the time with attractor, and everything is falling and turning. Everything.
Yeah, just turn gravity into geometry by making it a slice of a manifold. So, just different layers of abstraction, really.
So Alan, how far do you think these celestial objects are?
I have no idea.
No idea. Do you think there's any method you could use to figure that out?
No.
There's no method?
Nope. It all ends up being another ratio of another thing. So like for stellar and lunar parallax, it ends up being a ratio of Earth's radius, like whatever you define it as in the current modern units, whether or not that radius is like a physical, ball curve or a conceptual radius used to calculate for what it would come out to be. That doesn't matter. I have a, let's see if it's on my GitHub still.
Yeah, but what if you just do like a distance
no, just hear me out, bro. Just hear me out. So because they're all internally consistent units of measurement and ratios of angles, it doesn't It doesn't lead to a distance that's physically meaningful. Like, so in the Chinese system, it can be, the moon can be, I think, what does it come out to be, like 100, like 1,200,000 something lees, or you could have it be 285,000 meters or whatever, or kilometers, whatever it is. Like, it comes out as a ratio of what's observed versus what you're inputting for your coordinate system. So to get the unit conversion, so like to get a kilometer, to get a meter out of it, you have to put the radius in. So in both scenarios, the quote unquote physical dimension just comes out to be a ratio relative to your unit of measurement, which is defined by some other thing. And in this case, it's just defined by the angular change in position of stars over distance on the ground. So like, does it have physical meaning? Who knows? I don't think so.
Wait, are you trying to say though that parallax is not an accurate method of determining the distance to objects?
I'm saying
Just because
that, no,
we choose to use
no.
Because what
It's
you're
not what I'm
arguing
saying.
that you're just using.
It's not what I'm saying.
I would like to keep talking.
Jake, I know you would, but that's not what I'm even saying. Right? We're talking about parallax on the ground versus parallax measured in the sky for like solar lunar parallax. That's what I specifically said, because you were talking about distances to celestial bodies, not parallax measurements in general on the ground. I don't disagree with parallax as a valid method to determine things, but what I'm telling you is that
Why'd
the
you bring
ratio
up the
that you're gonna
Chinese
get out
units
of
then, though?
because those also apply to the celestial objects. And what I'm saying is that the units, the distance that you get out of it is going to be relative to the units that you're putting into it. And it might not have any physical meaning to it at all, but it is a calculated ratio that you get out of it. But it might not mean that that's the actual distance to it. It's conceptual. It's ratio.
It's not
based.
conceptual. I mean, it doesn't matter if I use
literally
meters
built
or
a model
miles or
off of
yards. It doesn't matter, right? I get my results back in
that's
meters or yards or miles, but those have a meaning in reality. They're not just conceptual.
Well, those are related to the coordinate system itself. A meter is 1/10,000,000th of a terrestrial meridian. The same way that a li is, I forget what it is, but let's say 1/16,000th of a li or whatever. So like, it's literally the same thing.
But a yard doesn't have any. It's not related to any coordinate system.
A yard is a ratio of the empirical system. You can unit convert them together. It's always going to come back to what it means for the meter, because that's what it was. That's what it started with.
Okay,
So,
okay, but
actually,
bottom line is it doesn't matter what.
Dude, that is the bottom line, bro. Because you're like all these different units, but they're all ratios of the coordinate system itself. That is my point. That's what the FE conceptual model was showing. Is that with internally consistent ratios, you can produce the exact same thing, and it's consistent to whatever your interpretation of how you believe it that is. So for whatever distance the li is defined by, so like, let's say we took a rope and made it a different length than what a meter is, right? And we related distance traveled on the ground to the angular change of Polaris in the sky. And once we had, say 300 or 500 lees worth of rope length that we traversed, that would be our conceptual definition of how far away we think things are. And it's internally consistent to that system. It doesn't have any physical meaning.
If that was true, you wouldn't be able to use parallax for anything useful because it's just conceptual.
Incorrect.
I'm just curious, why does parallax work for calculating the distance of things on Earth in units that we all understand what they mean and what they are, whether it's meters, miles, yards, feet, whatever, right? Why does it work on the surface of the Earth? What would be, and we know we assume the uniformity of nature, right? Like I assume that like being hit by a car here is no different than being hit by a car in China, right? Uniformity of nature, right? So what is your reason for believing that it wouldn't be? What is your reason? What is your reason for believing that parallax wouldn't be a useful tool for establishing the distances to celestial objects?
Can you repeat what my argument was?
You said that it just comes down to the ratio of these angles that are internally consistent, and that if a Chinese decided to say this length of rope is 5 Kwong Lees, then you'd have your result in Kwong Lees, and it's just purely conceptual. It has no bearing to reality. Something along those lines, I think, is what you tried to say.
Yes, when applied to the sky, yes.
Why would the sky be different than applying that to the surface where it is useful, or even to an airplane, which would be in the sky, right? You could use that.
Never verify it yourself. No, different observers get different altitudes when they do trig to an airplane.
Okay, but for example, if you do a parallax measurement to the moon, you get a certain distance, and then you can bounce a radio signal off of the moon and use the speed of light and calculate the return time. And you can say, well, how do you know that the speed of light is the same all the way to the moon, that it's not slowed down? And it's like, okay, well, we're just making that assumption because it doesn't appear there's anything in the way. And for some strange reason, it yields back the same value as the parallax measurement does, which is just an independent line of measurement from the parallax that also gives you the same. So at that point, why would you not consider that to be a valid form of determining the distance to something?
Well, when you get into measuring the distances using radar, what they do is they turn the detector off and on based on the interval at which they expect to get it to return, and then they get a noise, basically noise, and they try and extrapolate what the signal would look like from that noise under the time window that they opened it up into in the first place. So there's a whole thing showing how all of that's contradictory. And
I'm just
actually
talking about doing a ham radio bounce with a Yagi. I don't know. Do you have a ham license, by the way?
No, I don't have a ham license.
Okay.
Just
do you know how to do a moon bounce? Hold on a second.
God,
do you know how to do?
Jake. The thing is that the units in relation, right, is like this is all covered in the units of measurement down to the speed of light as well. And those units, right, to come up with that distance, why I say it's not physically meaningful is because you can derive the speed of light in the Chinese units as well. You'll get a different conceptualization of how far you think that distance is. It's not that when I say it may not be physically meaningful, is like you can't go and verify it. Only terrestrially can you go and verify it. When you're introducing other things of bouncing things and whatnot, I don't know very much about the moon bouncing ham thing. I'm told from Bull Knight that it's a real thing that can be done. I haven't looked too much further into it, but he said that he's done it himself, and I take his word for it. But regards to what that conceptual distance is, right? Suppose we did it all in Lee's speed of light, all of that, and did the same thing. We would have the same conceptual distance internally consistent to what we're interpreting it, because the speed of light, all of that is all interpreted through a ratio of a meter too, which is the same starting point. So it's never not a ratio of an internally consistent thing. And that's my point about when you look at it through the Chinese system or the system that we're familiar with, the result that you get for the sky might not be physically meaningful. The angle correction that you have to apply to get it to line up with the coordinate system terrestrially, for what they have fixed for the values, like, yeah, that gives you a number for sure. But is it physically meaningful? I don't know that it is, and there's no way for you to confirm that it is. So I'm going to unmute you now. Go ahead.
Well, first of all, the unit, I don't understand still again why you're bringing that up, right? If it's Lees or Longs or Quing Wongs, as long as we all know what that means, it could be done for useful things, right? We can build a house using Lees if we all agree on what a Lee is, and we establish what that length is, right? Against a standard unit of Lees, we understand what it means. And if something is 5,000 Lees away, we understand what that means and how many pavers we would need to make a road that's 5,000 Lees long. So it's completely irrelevant that we pick arbitrary units as human beings for units of measure, which is why we have so many different ones. We've had so many different ones throughout you talk all that time, Alan. I'm going to give my 25 seconds to finish what I'm saying. You have no reason for arbitrarily saying it doesn't work for the sky because you can't make, like, I guess you can't reach out and touch it, but I'm just telling you, you can use independent lines of measurement that have no reason why they should be consistent with one another because they're using completely different methodologies and they yield the same result. And you can't say, oh yeah, but that's just giving you a result in meters or kilometers or miles or yards or whatever. That could be anything. It could be, yeah, but you can build a house in any unit of measure that you choose to, right?
If you don't understand the internally consistent aspect of it, like if that part is lost on you, then you're not going to fundamentally understand the argument.
Well, the argument doesn't make any sense. We all agree that as long as we establish what a unit of measure amounts to against some standard, right? That's why they have originally they had whatever the house of measures where you can find the perfect centimeter stick or whatever, and all tape measures are based off of that. Then you could build anything off of that, right?
Neither system is any more correct than the other. They're all bound to the same thing: the angular position of the change of Polaris in the sky versus distance traversed on the ground. It's going to produce the exact same internal consistency.
That's not what we're talking about. We're just talking about the distance of celestial objects using parallax and using timing a radial bounce. None of which are at all. You could use the same measurement on a completely different planet, even a pizza flat Earth planet that's floating in space. It would still yield the same result.
What, dude? Okay, no.
Do you not agree? Why would it not? Why would a parallax measurement on a floating pizza, that if we imagine it's a thin crust pizza that has an unmeasurably thin thickness?
Jake, you're getting lost in superfluous details saying nothing. You're talking about the thickness of a pizza and shit. The original argument was about parallax angles and deriving distances based off it. It's an internally consistent unit that comes out of it. It might not be physically meaningful. Making different assumptions, you can get different things, right? The sun and the moon are the same size. The angular size is a part in determining that. So making different assumptions, you can have them be the same distance, right? But using the parallax, you can get two different distances when you compare the sun and the moon, but those distances are in different units are going to be internally consistent to the same conceptual change of position of Polaris over of the change of Polaris over distance on the ground. So you're not going to know if the moon is really, you're not going to have any real definition of 300 million meters to the moon. Shoot, I have my mic muted. If there's, I'll let you get your closing thoughts off on that, Jake. But if there's any other questions from anyone, please make those now, because we're going to wrap up soon. Go ahead, Jake.
I mean, you agreed with me that you'd probably agree with me that you could use a radial bounce to measure the distance to something on the surface of the Earth, and you could also use parallax to measure something on the distance of the Earth, to determine the distance of something on the Earth, right? I don't know why you're bringing units into it. The units are irrelevant. You agree that those
It
are
scales
valid
how
methods
far
for
you
determining the
interpret.
distance to
It
things.
scales how far you think it is to the celestial body. They have different. It gives different values in different units that are internally consistent. You just have the same starting point.
Okay, but
So it's not different.
we use different units all over the Earth, right? When we're in Europe and the US, distances to cities are given in different units, right? But we all know what they mean, and then we all know how much gas we need to get there, right? So it's irrelevant what the unit is. I still would like to know, why would you suddenly have this arbitrary reason for not accepting a combination of parallax and a radial bounce or a laser bounce to range the moon that yields the same result with two completely independent lines of information? Why you
I
would then
told you
jump to the conclusion that
I
those are invalid mechanisms?
Well, I started with telling you about the laser ranging method and how they interpret the bounce back and how circular that is. And then you brought up the ham thing, which I haven't looked into fully to see how that works.
Yeah, you send a
They
radio
can,
signal. You send a radio signal to the moon. You focus
that's
a
certainly
radio
what they
signal to the
say.
moon, and then you
That's
wait
certainly
for
what
it to
they
come
say,
back on your
Jake.
oscilloscope, and you look at the time data on the oscilloscope to see when the signal returned.
I don't even think that's what Bull Knight told me they do. So
there's a few different methods to do it.
Pretty sure it was about just receiving a signal, not having anything hooked up to an oscilloscope or whatever. But in any case, haven't looked into it fully enough to speak on the distance that it gets out of it. But what I can speak on is the internal consistence of ratios and using the lunar ranging, using the lunar ranging methods and how they turn the detector on and off to get it when they expect to get the signal, and how they try to interpret it through the noise, and how they also did the same thing with Venus measurements to try and get the position of Venus. So I'm not super worried about the internal consistency of that because it appears that those measurements didn't even, they don't hold up to any sort of scrutiny.
Where are you getting this that they're turning the detector on and off between firing the laser? And they're only turning it on at the exact interval.
Yeah, I'd have to get the paper from Taylor, but it's from from a paper that she referenced of how they do it. They turn it off and on. They did the same thing for the Venus ranging stuff. They would only analyze at a specific window when they expected it to be back based off of its position from the ephemeris. So they didn't do anything different in that regard. So I don't imagine it's different for the moon. But we can send you.
And it would make sense in that particular context. Yeah, in that particular context, it makes sense to me, because the reason why they use laser ranging over radar ranging, or using a radio signal, is the laser gives you centimeter precision, right? And so it makes sense once they know. What do you mean no?
No, dude, it's about them measuring an energy fluctuation in their detector out of the noise background and trying to interpret that as the physical reflection from the original photons that they sent. Because they'll say that they'll send out trillions of photons, but they just get back one singular one, which is them trying to extrapolate the measurement out of the noise. And to say that it makes sense to do that, it's okay, but what does the rest of the data set look like until then? How are we differentiating amplitude spikes of the noise background versus what was measured on your specific timing window, where you're trying to interpret one specific amplitude out of the regular noise floor from which the device was off at the first place.
They're looking for a very precise wavelength that matches the wavelength of the laser.
Yeah, and keeping it off and not showing the full scope of what the noise is, or including any magnitude scales in the diagrams that they show for these, is exactly why they don't have any meaning to, because you can't even differentiate the noise floor from the measurement. That was something that was extremely crazy to look at when they when they did the Venus ranging stuff, because that was supposed to be the most high tech modern way to do it. And they literally show you a graph of just curvy noise, and they're like, this right here is where the signal got boosted, and you can't tell. So your argument is that it's a good way to do it. They're looking for a specific thing. My argument is that when they present the data from the specific time that they analyze where they expect it to be is circular, and then trying to show it in terms of this is the magnitude difference of the noise floor, but not including any sort of way to interpret the magnitude on the y-axis, is it makes it meaningless.
Well, that kind of reminds me of my next question, something about being meaningless. Let's say if the government never accepts flat Earth until they're going to fight it to the bit there.
I'm going to mute you real quick, bro, because this isn't about whatever the government stuff is. This is mostly about future predictions of motion. So we're going to try and stay on task here about that. And we were discussing distances for some reason instead of future predictions of motion, and got a little sidetracked there. But you know, I don't have any problem entertaining that for a minute because it's actually something that I just added to the FE conceptual model. The update hasn't been pushed yet, but Dave McKeegan pointed out that there wasn't any solar or lunar parallax present in the model, and so I added it in the Chinese system. And so anyway, that's why I was saying that, you know, the distances might not be physically meaningful because it's just a ratio of the coordinate system. You know, it's going to be internally consistent because it's a ratio of mutually dependent constants that are used. So you know, keep that in mind. And then the physical measurements, let's say your best argument would be the ham thing. And like I said, I haven't looked into that fully yet, though. So we can come back to it on another time for another null. Actually, Jake, you know what would be super dope? For you to make a null hypothesis on that, right? And then we could have an episode on ham bouncing and like deriving distances.
What do you mean by null hypothesis? The null hypothesis would be, what are we going to define as a null hypothesis? Not receiving a signal back, or a signal that comes back far faster than expected of the theta distance? I mean, what would you consider the null hypothesis?
Well, the null hypothesis and hypothesis would be up to you mostly, but we could do something like you were just saying. Let's see here. They have to give it some thought, but the first one that you proposed didn't sound too bad about the, you know, does the distance match or whatever, and like analyzing the amplitudes or something like that. We can figure something out. Send me a DM. We could work on it together. How about that?
I'm still confused to, I mean, this is something that's very well established. I mean, exactly what are we going to be establishing as our null? I mean, we could say that, you know, ham operators claim they could bounce the moon off the sun with an expected round trip time of whatever, 2.5 seconds. We believe the Earth is flat and the sun is close and local, so we expect it to receive a moon bounce back in, you know, 0.2 seconds or whatever, and say, and the no result would be we don't. I guess maybe we don't receive anything at all. Nothing comes back at all. I'm not sure.
Yeah, well, the globe versus flat on that hypothesis would be slightly different because we have to, you know, through the analysis, right? Because like this is what we're just going off of, like what they claim, right? We don't know the conditions and whatnot, and there might be certain factors that go into it that make it, you know, word I'm looking for, where it might not necessarily be causally related to the moon, but just general position, something like that. So we'll have to look into, we'll have to, like, you know, fully explore it or whatever. But yeah, something like that.
I just don't really understand. I mean, for us to set up this experiment, we have to come up with a hypothesis. What's the hypothesis that we're testing? Are we testing whether the moon is 2.5 light seconds away from the Earth, or are we testing something else?
Whether it's 2.5 light seconds away from the Earth.
Okay. So we go and we do this, and it's 2.5 seconds. Are you now accepting the distance?
Well, like I said, we have to go over the procedures, how it's done, etc. Right? It's not just about does it produce the number. It's how is it produced, what conditions, so on and so forth. Like that's
if we're able to send out a pulse, and
hang on.
We'll pay for your ticket.
Jake, you're not listening. Not listening, right? We'll look into the procedures, how it's done, etc., the repeatability, so on and so forth. Okay.
Okay.
We'll do a presentation on it. We'll see exactly how it works.
Okay. If we show that the signal is
Jake,
coming back,
there's a lot of ifs here. And I'm trying to wrap up number one, right? And then number two, we're talking about something that's not even related to the primary null hypothesis.
Well, let's make it. Can we make it interesting? Can we?
Hang on 1 second, Jake. No, we really can't at this point. We've detracted from the initial point of all of this to talk about something completely unrelated. So the more that we go down this path, the more irritated I get because we have a specific goal and timeline in mind. We're now 2 hours into it, talking about a different thing, which gets super annoying. Now, your proposal, though, for the null hypothesis, right? You clearly know how a null hypothesis works. So I look forward to you putting together one for the moon distances and the ham stuff.
I've just been burned by flat earthers asking me to jump through hoops, and then in the end, it's a waste of my time because they're not going to respond in any way to my data, one way or the other. They're not going to make any response whatsoever, other than maybe say, "Well, it could be some mysterious, could be an alien that's somehow grabbing the signal and returning it." I mean, that's just a waste of everybody's time, right?
Oh, the irony.
If you're willing to
No,
put
it's
something up for grabs, I'm willing to put.
Jake, it's a null hypothesis. They're two mutually exclusive outcomes. There can't be an alien doing the thing or whatever. You either falsify the null or you don't. Okay? So it's pretty straightforward. You're saying additional things now that have nothing to do with a null hypothesis. Like people not looking at your data is a separate issue. Other people not arguing with it, separate issue. Falsifying the null hypothesis is the determining factor. If nobody can do that, then what they say about it is irrelevant, Jake. That's the power of it. So I'm gonna unmute you now and say good night to everyone. Good night, everyone. Good night, Jake. All right, everyone. Thanks for
Good night, Alan.
hanging out here. Thank you, sir. Thank you guys for hanging out here at the Null Hypothesis for Monday. Sorry we got a little distracted there at the end. I do want to try and keep it to the exact actual point, but I don't want to be rude and not, talk about other stuff towards the end. But hopefully this will lead to another Null Hypothesis follow-up episode that we can do. So we look forward to fully flushing that out. So we'll get into that as it continues.
Thank you, Alan, for taking the time to present.
Yep, no worries, lad. And if anyone would like the document here used, I will put it in the main chat so you guys can review it and have it for yourself. It's an isolated HTML file. It doesn't require any additional files or folder structure or anything like that. You can just launch it in your web browser and it will have everything here as is. Okay. All right, lads. We'll see you guys on the next one. I'm going to end stream here. I'll be right back.
I still have many questions, but hopefully reading the document will help me ask those questions better next time.
Thank you, Gio. Yeah, Zizi, it's interesting because it's like something's moving, right? Either the Earth or the stars in the heavens. So if the Earth is stationary, I mean, it's pretty interesting. It would be interesting to be able to understand the moving sky like really well, the ins and outs.
Yeah, I did miss a little bit because there was someone at the door and the dog was barking. So it's possible I was misunderstanding or missing the point of something when I came back to ask the question later. I do have to get going for like the next hour or so, but I think I'll have some more time to jump back on later and would be particularly interested in discussing the stuff and maybe getting a little bit caught up on anything I missed in Alan's presentation when I was up dealing with the door later with anyone who's on later tonight.
Awesome. Thank you. Have a great one.
Yeah, thanks.
So, Gio, are you here by chance or anyone? Because I'm wondering, do you know how they say on the flat Earth model, you'll see when the sun goes around the... Oh, hi.
What's up?
Oh, thank you. So, Alan, I really appreciate your time. And you remember how you were saying how the sun accelerates around, I guess, when it's going around the curve? Could that possibly be explained on a planar surface when the sun is maybe not on the... Well, it's above maybe the Tropic of Capricorn or maybe the inner ring, and where it's actually accelerating when it's on the outer ring? Or what are your thoughts, sir? Thank you.
Not really sure what your question is, big dog. Sorry.
Oh, my bad. Okay, so do you know how they say
you're good.
on the... Thank you. Do you know when they say maybe on a planar Earth? Oh, wait, actually, I guess there's several options. I wonder if you're into a dual pole. I don't know what your position is on a planar.
Not particularly. I think the way we perceive the sky is just a facet of our optics, but willing to be wrong or whatever.
Likewise, thank you. I'm actually with you there. So, okay, thank you. On a planar world with maybe one direction of the sun, while it goes around the plane, above the plane, do you think it changes speed throughout the year as well? Like, but not in the way that the globe was doing?
Oh, I see what you're saying. So, what's really interesting is in Gleason's book, he talks about how to calculate distances between longitude on his, using his projection. And so because the longitude lines are straight lines and the rest of it, is concentric circles curved outwards that get increasingly stretched out, that it creates like a visual distortion, right? But he was talking about how his map came with this little thing that hangs from the center, it's like basically a ruler, and you mark points on it, and then you calculate the timing difference between them, and depending on whether or not you're in the north or the south and the time of year, there's a different rate for the 15 degree per hour for the sun to use or whatever.
Wow.
And then he was saying that if you use the mean between them or whatever, like the equator velocity, which would be like I think 900 kilometers an hour or something, whatever it comes out to be, or 900. I forget what it is, but it's like 1,000 miles an hour or whatever. Anyway, if you use that value, it maintains like the 15 degree per hour symmetry, and it doesn't. You can just use that instead of using the respective north-south values. And then another instance where I found that, kind of just recalling from memory, Jaren got a call in from this woman named Orphan Red. I don't know if you're familiar with her.
Oh,
She
yes.
called in on his show one time to talk about how she found this paper where they were talking about the change of the speed of the sun versus the summer and the winter and stuff. So, yeah, I mean, it's just apparent motion, right? So causal mechanism is unknown, but it definitely seems to occur.
Totally. Thank you. I really appreciate that.
Yeah, no worries, lad.
Seems logical.
I think I have the clip. I think I have the clip on my channel too of Orphan Red talking about that. Give me 1 second. I'll see if I can pull it up.
Wow. Thank you. I hope she's still a flat earther. So yeah, because it makes sense, right? If they say the sun is going to accelerate on its elliptical path, then obviously, let's say if they're lying, I mean, it makes sense that there's got to be another explanation, and that seems to match what has been said about the flat Earth sun trajectory. And it makes sense that people would have noticed the differences in speed and recorded it.
Yeah. Damn, I can't find the video on my channel, but I can send you Gleason's book if you want to take a look at that section.
Oh, yes. Thank you.
No worries. All right, the book is in the main chat, sir. It's uploading now.
That's great. Really appreciate it. I'm trying to think of what mechanism would cause for the sun to speed up. Could it be the Earth it's traversing? Something about the Earth? Because the USGS says the Earth has some sort of permanent magnetization. And I wonder if that could, just like on these speed trains, you can adjust the speed, of the, I guess, by maybe adding some more electricity or magnetic force, electromagnetic. Yeah.
Yeah, I don't know, and personally, I don't think we'll ever know like why the objects in the sky moves. That's been like the whole cosmological battle, right? They took a ratio of pi and periodicity and turned it into another ratio and said that ratio is the cause of the geometry that the first ratio produced, which is it's like okay.
Okay, yeah.
Yeah. So if you go to page 321, talks about the sun's motion centric with the polar center. I think that's what you'll be looking for there.
Oh yeah, definitely. Thank you.
All right, lads. I'm gonna head off and play video games and watch anime or whatever it is I do. We'll see you guys next Monday for the old null hypothesis. Maybe we'll do a little follow up to this one. But I think next week we'll introduce a new subject, unless people have follow ups or stuff from this subject or from this week. So some homework for the lads. Dazzle was talking about integration over the sum of all the gravitational bodies or whatever. So hopefully that can be brought up and addressed next week, and or not or whatever. We'll see what happens.
That would be a good subject.